In the next three sections, we consider two very important laws due to Gustav Kirchhoff, who was a German physicist in the 19th century. And this deals with looking at circuit analysis from the relationships between voltages themselves or currents themselves. And so we start off with the concept of a node in a circuit. A node is just simply a connection between two circuit elements, basically conductors or the wire connections. And Kirchhoff's current law, which we refer to as KCL, states that the net current entering a node is always zero. Or you could phrase it as the sum of the currents entering a node always equals the sum of currents leaving a node. You can also look at it in terms of the net current leaving a node is zero. That's another way of looking at it. So there's actually three different ways you can think about this. So we're going to illustrate this KCL, Kirchhoff's current law, with the following three examples out of example 9 on page 11 of the workbook. And we'll start off here with node A. And you can see here you have three circuit elements and you have a current flowing from left to right through the circuit element toward A. You have another current I2, this was I1, this is I2, coming from the bottom up to the top of this circuit element and coming into node A in this direction. So these are two incomings, and this is a representation of an outgoing current, I3, coming out of that node. So if we write KCL in terms of just strictly, let's sum all the incoming currents, they should be equal to zero. And that's what this equation here is representing. I1 is an incoming current, I2 is an incoming current. Now I3 is not, so we'll indicate that by -3. So minus I3 means that's the representation of an incoming if in fact the reference direction is opposite of an incoming. So in this case, I1 plus I2 minus I3 equals 0. Now another way of seeing this is that clearly the incoming currents are 1 and 2, and the third one, I3, is outgoing. Notice the sum of the incoming equals the sum of the outgoing, right? But all you have to do is, if you're just trying to sum up all the incomings and you have an outcoming current, just switch that outgoing current in terms of its sign. Similarly, look at node B. You have an incoming and an outgoing. So if we wrote this as a representation of summing up the incoming currents to a node and set it equal to 0, we'd have I3 minus I4, because in this reference direction, the incoming current would be minus I4 because the reference direction is actually away. And then finally in node C, you actually have three incoming currents. So there's no need for a sign change. I5, I6 plus I7 must be equal to 0. All of these are representations of KCL applied at all these nodes, right? But as I indicated earlier, also, you can represent it as the net current leaving a node. So there's various different ways, just depends on what's easiest for the circuits you have. So let's flip the page and look at just representing the same examples we just had a minute ago, but now representing them from these different perspectives, okay? So I'll just briefly sketch them again, just so that we have this on the page so they're available. So the A node simply was, and I'm just gonna write it from the perspective of the currents and leave out the circuit elements. So from the perspective of A, we had an incoming I1, and we had an incoming I2, and we had an outgoing I3. And for node B, we just had an incoming I3, and we had an outgoing I4. And then finally with node C, here at the end, we had three incomings, right? It was 5, I5, and then on the right was I6, and then coming in here was I7, okay? So that's just restating what we had on the other figure in the previous page. But now we're going to represent KCL from the perspective of outgoing, right? So this is KCL from the perspective of outgoing currents. And of course, in this case, what we have here is if we're only looking at outgoing currents and summing them equal to 0 for Kirchhoff's current law, then clearly to represent the first outgoing current, we'll need to use minus I1, right? Followed by a minus I2 because the reference direction is towards it. And then I3 is in fact an outgoing current, so plus I3 equals 0. So that's what we would have for node A. And then if we had the representing outgoing currents for node B, there's only one I4. So the other one, we need to flip the sign. So we'd have minus I3 plus I4 equals 0. Again, basically the same equation we had earlier. And then finally for node C, if we're representing completely outgoing, then we have to change the sign of all of them. But again, if you just moved all these components on the other side of the equal sign, you'd have the same thing we had a minute ago. So you can represent the sum of incoming equals 0, the sum of outgoing is 0. And then finally, you could just represent the fact that incoming has to be outgoing. So this is just another traditional way of saying the sum of the incoming currents has to equal the sum of the outgoing currents at a node. Okay. And so clearly from an A's perspective for node A, again, these are all the same equation, just thinking about it differently. Clearly in this case, the two incomings are I1 and I2, and the outgoing is I3. Again, exactly the same equation over there, just a different perspective. And then node B, that's just I3 equals I4, isn't it? Yep, because there's only one incoming and one outgoing. And then finally for node C, you have no outgoing currents, right? So from the perspective of incoming, you have I5 plus I6 plus I7 equals no outgoing currents, okay? Again, same as the other two representations. Okay, so it is important to note that all nodes in a circuit that are connected directly by conductors are a single node. This can be a source of contention sometimes. We have to be careful. So we're going to look at this example as a prime illustration of what to be careful about, all right? So when you look at the connections here between these four elements, what one might think, because of the way those little circles are drawn on this straight line here, that you have three nodes. Well, in fact, you only have one node represented here, okay? So there's only one node because there's no circuit elements in between all these connections. So if all you have is conductors all connect to each other, you consider that a single node. So this again is just one node right here. Okay, that's how we think of this. All points or nodes directly connected by conductors is a single node. There's no circuit element in between them, okay? So in this case, if we use KCL, you have an incoming IA and you have IC and incoming. You got two incomings, two outgoings. So in fact, there's the appropriate equation we need. IA plus IC must equal IB plus ID, right? Now, if the circuit elements are connected end to end, they form what we call a series circuit, and the same current flows through each element, okay? So for example, this is a representation of a series circuit because you could think of it as a daisy chain, that you're chaining all of these circuit elements one after another. So we've illustrated here three different currents: the current that flows through A, the current that flows through B, and current that flows through C. But in a series circuit like this, all of these currents are the same. So there's only one current flowing through all the circuit elements if they are in series, okay? Right? Or another way of looking at it is simply from KCL. Incoming is outgoing, and so the outgoing, the incoming of this node has to be IA and the outgoing is IB. They have to be the same. So it's not hard to see that IA has to be IB, IB has to be IC, therefore you must have IA equals IB equals IC, okay? All right, let's do another example just to make sure that we're clear on interpretations of KCL. So we're going to use in example 10, the bottom page 12, KCL to determine the unknown current. So we're labeling one particular current we're interested in, and we're looking at these representations of connections, all right? So the first thing we notice in the first example is we do in fact have one node represented by the incoming currents are coming in, or either coming or going from one position here, all right? So from a KCL perspective, you have two incomings, you have 1 amp plus 3 amps must be equal to the outgoing amp. So it's very simple that IA must be equal to 4 amps, okay? Now, if we look over here to this perspective, even though we have two joints here, again, this is one representation of one node. That again is one node because there are no circuit elements between those connections, okay? And so in this case, if we look at, we can look at incoming currents. We have, in fact, we have 3 incoming currents. We have 3 coming in, we have 2 coming in, and then this mysterious IB coming in, right? And the only outgoing current we have is 2. Excuse me, this should have been 1, sorry. So we have 3 plus 1 plus IB equals 2. Again, 1's coming in, 3's coming in, IB is coming in, and 2A's out. So if you sum for IB, clearly you're going to get, this is 3 plus 1, which is 4. So you're going to get 2 minus 4, which you're going to get minus 2 amps, okay? So the current coming in here is minus 2 amps, right? And then finally, one more time, again, this is a representation of one node. There are no circuit elements between those connections, okay? And we have 4 currents that are all incoming, okay? So there's 1 incoming, there's 3 incoming, there's 4 incoming, and this magical IC is incoming, and there's nothing going out, okay? And so quickly we can see that we would need IC to be minus 8 amps, right? So just be careful about looking at connections and making sure you're taking the right number of nodes to measure the currents with, okay? All right, so let's go on to page 13. Okay, and we're going to the next voltage, the next law Kirchhoff discovered is the voltage law, how we can represent algebraic sums of voltages in a current, in a circuit, right? So again, KCL, incoming current must be equal to the outgoing current for every node. Kirchhoff showed that the algebraic sum of voltages is always equal to 0 for a closed path or a loop in a circuit. So that's important to realize what we're talking about. It must be a closed path. You don't have a break in the conductors. You don't have an open circuit anywhere, right? So, so the algebraic sum of the voltages in a closed loop has to be 0, relates to the conservation of energy, okay? So let's write the KVL equations for voltage in the following 3 loops, and you can see we'll write them in a way that we can represent the loops. I'm going to use a different color pen here so you can see them. So the first loop, we'll look at this loop here with A, B, and C. So let's call this loop 1. And then we'll look at this next door to it, another loop, L2, again from C, D, E. It's a closed path. And then you'll notice we also have go around to the outside from going B, D, A, and E. That is another closed path. So there's 3 closed paths here that we can represent, right? So if we do that, let's look at how KVL applies to each one of these loops, okay? Right? And we need to pay attention when we move along the path, pay attention to voltage polarities in terms of if we were moving as following the current, are we in PRC or not, right? So if we go around, let's take the first one. So we're going, I've drawn it, it doesn't matter which way you do it, but I'm trying to, in this case, I'm representing it clockwise. So if we were flowing with the current this direction and we came into the negative polarity of minus VA, all right, then the voltage we would be representing is minus VA, okay? So again, it's not PRC. And then we would come into the positive pole for VB, see? And then we would come back into the positive pole for VC, okay? And KVL means the sum of those must be 0, okay? Again, you'll change the sign of the voltage if you are entering, as you traverse the path, if you're entering the negative polarity, you're going to represent that voltage, same magnitude, but you're going to change the sign of it. Okay? Again, if you go loop 2, again, we've represented clockwise. It doesn't really matter which way we do it, okay? But it's good to be consistent. But in this case, I'm going to show you both ways. These two we're going to do clockwise. The other one we're going to do counterclockwise. So if this one is clockwise, we're going to come into the negative pole for the C element. So we'll say represent its voltage minus C. Then we're coming up through D, hitting the negative polarity minus VD, and then coming into the positive pole for the element E. So that will be a PRC representation. And again, that has to be 0. Or in other words, that the voltage in E has to be the sum of the other two, okay? Finally, with 3, we're going around the outside, and we're going to go, and maybe it's sometimes useful to say how the KVL loop was executed. So those two were clockwise. And this other one, we're going to go counterclockwise or anti-clockwise, okay? So it doesn't matter where you start, but let's just start at A. If we're coming counterclockwise, we come into the positive pole for circuit element A, so the voltage representation is VA. Then we're coming around to the negative pole for E, minus VE, right? And then we're coming back into the positive pole for D, so that's VD. And then we're going to come into the negative pole for B, so minus VB equals 0. Again, in a counterclockwise path, right? So just as important to realize, how you are traversing it in terms of, if you went the other way, all the signs would just be flipped, but your equation would still be the same. So there's no right or wrong. Just pick a direction. Just pay attention to the polarity that you would be hitting first. Okay. Now, according to the law of energy conservation, the sum of the power in a series, as we're going to show, must equal to 0. So the power from conservation energy standpoint must be 0. All right. So we'll look at the example and then look at these equations again. Okay. So we're flipping over to page 14. Okay. And so on page 14, we have this circuit up here. Okay. 3 circuit elements. Polarities of the voltages are represented, and you can see the current flow here. These are definitely in series, and notice that we have labeled all of the currents the same. They're in series. Remember, A, B, and C are in series. Therefore, there's only one current flowing through them all, okay? So if you're going to represent power here, okay? So in other words, let's represent the power associated with circuit element A. It should be the voltage times the current. So in this case, that would be the voltage A, VA. It's definitely in PRC, so that's times I. Again, it's PRC because the current is flowing into the positive pole of the voltage. And let's do B. Power for circuit element B. The current is flowing from the bottom to the top, and it's coming in through the negative, so this is not PRC, okay? So we get a minus VB, so we could even make a note. That's because it's not passive reference, okay? And then finally, the power for element C. Again, the current is flowing into the positive voltage polarity, so there's just the same formula as A, but it's VC times I, okay? Right? Okay. And if we were to sum these up, so what we can see is that let's go ahead and sum these. If we sum PA plus PB plus PC, what we would in fact have, because we can factor out the current, right, times I, right? So you see what's happening because that is a common component to all the circuit elements, all right? And so what's interesting here is that we already know from a KVL standpoint, right, that as we flowed in a closed path, in this case we were going clockwise, all right, we know that this summation, well, I'll just say this equation here, VA minus VB plus VC, right, must be equal to 0, right, according to KVL. So therefore, the sum of the powers must be 0. Law of energy of conservation, okay? So, so that's important to realize that you can always sum the powers and get 0, and maybe use that to help determine voltages and or specific currents as well. Now, it's important to know that the reason why this, assuming that the current wasn't 0, the power has to sum to the 0 because of the series representation of the elements, right? That it was just one current there. But if you take a different topology for your circuit, which is in the next section, looking at parallelism here, you can wire up or connect elements in parallel, right? And things change a little bit in terms of properties of currents and voltages, all right? So here's a representation of a more complicated circuit. And the idea of two circuit elements being in parallel, if both ends of one element are directly connected to the ends of another element. So the two ends, whether the two tops or the two bottoms, the two lefts, the two rights, however it's configured, if they're connected, they're in parallel. So if we look at scanning left to right, clearly A and B are in parallel. Right? Now, you may say, well, wait, is B and C? Well, no, because their tops are connected, but their bottoms are not, because there's other circuit elements in the way. But D, E, and F certainly are. If you change pens here. Oops. Okay, there we go. So there's two sets of parallel of circuit elements, right? So now we're going to look at a partial circuit below and then look at the relationship between voltages when your circuit elements are in parallel, right? So remember, you had the same current flowing through elements in series. What will we find out about voltages in the case of parallelism of circuit elements? And one thing to notice about this particular illustration down here is that this circuit is open over here. This is not a closed path. You have closed paths in these loops inside, but it doesn't necessarily have to be on the outside here, right? And so we're gonna look at two loops here, right? This loop right here, it's a closed path, L1, and then we'll look at L2 going, let's say, this is going clockwise and we're going around all three of them, okay? So I'll draw it like this, is L3, okay? So, so we're going to involve A and B for loop 1, and then we're only going to involve A and C for loop 2. Do you see that? So it just depends on the closed path you want to go on, okay? Right? So if we're representing KVL on loop 1, okay, and we're just involving these two circuit elements A and B. As we go clockwise, right, imagining the current's flowing this direction. So if we're flowing in this direction, we would not be PRC here, right? So we would be representing a minus VA voltage, right? And then we would come over into the positive pole for B and plus VB. And according to KVL, that must be equal to 0. So another way of saying that is that those two voltages must be the same. Interesting. The fact that these are in parallel, the voltages are the same. Okay. And if we look at L2, we're going through A and C, same thing. You are not PRC as you come into A, and then you come into C, you are not either, okay? So that's minus VC equals to 0, okay? So what this says is that, we pull VA over, is the VA is minus VC, okay? So it's interesting that the two voltages are the same, exactly same on A and B, VA is the same magnitude, but not the same sign as C. The voltage for A is the same magnitude, but not the same sign as the voltage for C, right? But what we're noticing is that when these items are in parallel, the magnitudes, not the plus or minus, the magnitudes are all the same. So it may not be that everything has the same, 5 volts. One might be 5, one might be -5, things like that. But the magnitudes will be the same if they're in parallel, okay? And we're going to do one more example just to make sure we see this situation, all right? All right, we're going to use KVL to determine two voltages at the bottom of page 14 on example 11. VC and VE, we'll see that in the diagram next. And we're asking which circuit elements are in parallel and which are in series, right? So this is again at the top of page 15 now. There you go. Clearly, you can see the dynamic we have here, all right? Okay. We're interested in getting VE and VC, okay? This was the diagram from the previous one, okay? One thing that's important to realize that I just glossed over is if you go back to the original diagram on page 14 for this figure 6, you'll notice that sometimes what we can do is we could represent one voltage polarity, okay? Typically, we can use the same reference polarity for the entire parallel circuit, all right? Even though, the magnitudes are the same, but even if the representation of the polarity, if the polarity differences were slightly different, most of the time, this is what people will do, okay? It's very rare that anyone was going to hook these things up in this way, where the polarities are not the same, okay? So this is not typical. Typically, this is what one would do, right? You would put them in parallel, and then the fact that we know the voltages are all the same will actually assign the same polarity to all the top terminals and the bottom, okay? So this is much more traditional way than the previous example, okay? And then you don't have to put pluses on each top here and minuses on each bottom, right? So that's important to realize. Now let's look at our example. Okay, so we're going to look at loops here. Again, with KVL, you're applying loops, right? If you needed to figure out this voltage here, all right, you're probably going to look at the fact that, oh, I've got two other voltages available in this loop. So let's define a loop here. Let's call it L1. And then you're interested in this voltage over here for VE from this circuit element E, knowing that, if I can figure out what the voltage is for C, I've got this one and this one, so let's let this be another loop too, okay? And see if we, again, taking two known items and finding the third because of the sum being 0, right? So let's go to loop 1, okay? And again, we're doing KVL, we're doing it clockwise. In both cases, we are doing it clockwise, and it's good to indicate the direction in case we're needing to debug something or look at someone's work and figure out their analysis. So the voltages as we go clockwise, negative terminal there, so -3 volts coming into the negative polarity there, -5 volts coming into the positive pole here, that's PRC, plus VC must be equal to 0, okay? So clearly what that says is that VC must be positive 8 volts, right? So then now moving on to loop 2, since we now know that VC is 8 volts, we look at we go through the closed path, paying attention to voltage polarities as we go, coming into minus the negative polarity here for element C, it's 8 volts, so we should have minus 8V. Coming into the negative polarity for that 10, minus 10 volts. And you know, it might be important to recognize the fact that um, this actually was given, this is kind of tricky here. This was actually given as negative 10 volts, right? So it's fact, what we really have is minus, I'm gonna scratch this out, minus 10 volts. Interesting. This is not a typo. It's just if they're telling you this is negative 10 volts, and then we are coming into the negative pole, we know we have to apply a minus sign. In fact, we're going to be adding 10 volts, right? And then we're coming into minus VE equals 0. Very tricky, isn't it? Okay. So we have to be careful about that. Now, if this had been plus just a regular 10 volts, right, then we would have had just minus 10V here. Okay. But in fact, what we have is minus 8 volts plus 10 volts minus VE equals 0, right? So in fact, minus 8 volts plus 10 volts must be equal to VE. So in fact, VE is just 2 volts, okay? And so those are the two quantities we want. So we just have to pay attention sometimes to, you know, what quantities we're given. Most of the time, you're working at your representation of voltages will probably be positive, but you know, it's possible that that could be given to you. Now, if we're trying to identify relationships between these circuit elements, again, do you see circuit elements chained end to end? And I think you can here, right? You can see that A and B are definitely in series. In other words, as you leave A, you must fully go through B. If you went the other direction, B, you must go into A. And then you might ask the question, well, wait a second, how come you didn't add C, right? Well, because B does not necessarily have to go into C. See there, it has a bypass, it has another exit. There can be no exits in series. You must be forced into this path, right? So the fact that there's a branch here, another way to flow, C cannot be in series, okay? Same thing with A. E could come into A as well as C coming to A. So there's no guarantee you're coming into A exclusively through C, all right? So only A and B are in series. And then let's look at the argument for parallel. Well, if you go from right back to left, it definitely looks like E and F are in parallel. And then we might ask the question, well, should C have been added to that? Well, again, they're not connected. Their nodes must be connected end to end. You've got D in the way, okay? Same thing, A and C can't be in parallel because you have B in the way. There can be no circuit element separating their terminals, okay? So just be pretty careful when you're identifying series and parallel. And that ends the discussion for Kirchhoff's law, and then how series and parallel circuits can help us simplify representations of current and voltage.